All right, so now given that we have a topology on a topological space, we can start talking about the idea of continuity and connectedness. Okay, so all right, so let me first talk about the idea of continuity. So let me give you a definition. So a map F between two topological spaces, say from X to Y, right, where X and Y are topological spaces, so they don't have to be subsets of each other, right? Right, is continuous. Okay, if the preimage of every open set is open. Okay, all right, so that's sort of the, it's like the most abstract version of continuity. It's like we can introduce. Okay, and as you will see, it's like this notion of continuity. It's like then allows us to introduce the idea of a path. Okay, so with the notion, well, let me put a bit of space. That's not part of the definition, right? So with the notion of continuity of continuous maps. Right, we can introduce the notion of paths and path connectedness. Okay, so how do you go about doing that? So let me define for you what a path is, right? So a path is just a continuous map from the closed unit interval. It's like to the space, right? So a path is a continuous map let's call that gamma from the closed unit interval, right, to the space X. Okay, and as with the case when we were talking about graphs, right, so when we talk about paths, it's like on a graph, it was possible for vertices to repeat themselves along the path, and so we want to allow for that possibility when we talk about paths here. So, so as with paths and graphs, right, we allow for self-intersections. Which basically means that there can exist points or times s not equal to t, such that the point that's like in x, it's like which is associated with s, is equal to the point in x which is associated with t. Okay, and then of course if there are no self-intersections, then f is injective. And gamma is a simple path. Okay. So the notation or the here is quite consistent with what we've seen before. It's like when we were talking about the idea of paths and path connectedness in graphs. Okay, so with that, we can talk about the idea of a space being path connected. Okay, so a topological space X is path connected if every pair of points is connected by a path, right? Which is sort of a fairly obvious notion of path connectedness. Okay, and if you recall, it's like we also sort of had this idea about taking a graph and being able to separate it into disjoint sets of vertices with property that there's no edge in the original graph, which connects vertices in one of those subsets with vertices in the other subset. Okay, and so we're going to do something similar then in the context of topological spaces. Okay, so let me define that for you. So the definition then is that a separation of a topological space X, right, is a partition of X into two sets U and W, such that the disjoint union of those two sets gives you X. Okay, and you want to partition this into two sort of non-empty. So if you recall, it's like there was a notion of non-trivial, it's like partitions, it's like with the graphs, right? And so the non-emptiness condition gives you this non-triviality. All right, two non-empty open sets, and they have to be open sets. Okay, and then as you might expect, if you can't separate a space, then you say it's connected. Okay, so a topological space is connected, right, if it has no separation. All right. Okay. So the first thing it's like you should observe, it's like when we define this, is that we've made a distinction now between path connected, where we say that every pair of points it's in the topological space is connected by a path, with this notion of connectedness, which is basically about the non-existence of a separation. And so the natural question to ask is, to what extent path connectedness and connectedness are related to each other? Okay, so let me say something about that. So what turns out to happen, basically, is the following. So the remark is that, for topological spaces, right, this idea of path connectedness implies connectedness. Okay, but as you might imagine, it's like if I write something like that, it's like then the converse is not true. Okay, but sort of connected does not imply path connected. Okay, and then you might ask, it's like, well, what are examples of something like this? So there's an example which is called the topologist sine curve, right? So for example, sine curve okay, which is this set, let's say X, right? It's the union of the origin. So think of X as being a subset of R2, union of the origin with the graph of a function, okay? So I'm going to say X and the point sine 1 over X, okay, where X is in the half open interval from 0 to 1, okay? And then of course this is a subset of R2, okay? And then you have to of course endow this space with a topology in its natural, since it's a subset of R2, to endow it with the subspace topology, okay? So with the subspace topology, okay? Then of course this makes X a topological space. And then that allows you to talk about this idea of connectedness and path connectedness. Okay, so anyway, so if you have this topologist sine curve, right, then this is connected, but it's not path connected. Okay, so that's sort of a counterexample, if you will. It's like which says that connectedness doesn't imply path connectedness. Okay, so that gives you again sort of this brief overview of how it's like the notions of topology, relate to this idea of connectivity and connectedness. Sorry, continuity, it's like, and connectedness. Okay, and then with that, it's it's like in a position to start talking about what are the things it's like one can do, it's like in order to operate, it's like on these kind of topological spaces, it's like, and their discretizations, if you will. Okay, so I'll stop here for now.